Welcome to the Hypnos Sleep Channel. Tonight, Hypnos, the ancient Greek god of sleep, will guide us gently through one of the most beautiful questions in space science. Could human beings ever build a warp drive? For now, imagine the night sky as a map that has not yet learned how to fold. The stars are there, steady and quiet, but they are separated by distances so large that even light needs years to cross them. A radio message to the nearest star would not arrive for more than 4 years. Light from Andromeda has been traveling for about 2.5 million years before it reaches your eyes. The universe is open in every direction, and yet, by ordinary motion, it is almost impossibly vast. This is the dream behind warp drive. Not simply speed, not a rocket becoming brighter and louder until it outruns light. A true warp drive, in the most careful scientific sense, would be an attempt to move by changing the shape of space-time itself. The ship would remain locally inside a calm region, while space in front of it became shorter and space behind it became longer. It is a doorway idea sitting between science fiction and mathematical physics, and it asks whether the cosmic speed limit can be respected locally while distance is rearranged globally. The first anchor is the speed of light. In special relativity, light in a vacuum has the same speed for all inertial observers. This is not just a fast number. It is part of the structure of spacetime. As an object with mass moves closer and closer to light speed, its energy requirement grows without limit. Ordinary matter cannot simply accelerate through that boundary. A spacecraft can become very fast, but as far as known physics tells us, it cannot locally pass a beam of light moving beside it through empty space. Our fastest real spacecraft shows how far we still are from that edge. NASA's Parker Solar Probe, diving close to the Sun, has reached about 430,000 miles per hour during its record-closed solar passes. That is faster than any human-made object has ever moved, and it is still only a tiny fraction of light speed. Parker is an extraordinary machine, protected by a carbon composite heat shield using repeated Venus flybys to fall inward toward the Sun. But even Parker, at its record speed, would take thousands of years to cross the gulf to another star. This contrast is useful because it keeps the warp question honest. The obstacle is not that engineers have failed to build a big enough engine. The obstacle is that interstellar distance belongs to a different scale. The Moon is a few days away by spacecraft. Mars can be months away. The outer planets can require years. The nearest stars are light years away, and a light year is the distance light itself crosses in 1 year. To make star travel feel like a journey instead of a civilization spanning inheritance, something deeper than ordinary propulsion would be needed. General relativity gives the dream a narrow mathematical opening. In general relativity, gravity is not treated as a simple pull through space. Gravity is the curvature of space-time. Mass and energy tell space-time how to curve, and curved space-time tells matter and light how to move. This is why the Sun bends the paths of planets, why black holes create horizons, why clocks tick differently in different gravitational fields, and why gravitational waves can travel outward as ripples in space-time itself. If space-time can curve, expand, contract, and carry waves, it is natural to wonder whether a small region of space-time could be shaped into a moving bubble. In the mid-1990s, physicist Alcubierre described a famous mathematical solution inspired by the warp drive idea. In that solution, a spacecraft sits inside a relatively flat interior region. Space ahead of the bubble contracts. Space behind the bubble expands. From far away, the bubble could seem to cross distance faster than light, while the ship inside never locally breaks the light speed rule. That distinction matters. In cosmology, space itself can expand in ways that make very distant galaxies recede faster than light, without those galaxies flying through their local neighborhoods faster than light. During the early universe, inflation is thought to have stretched space extremely rapidly. Even today, because space expands over enormous distances, there are galaxies whose light emitted now will never reach us. Expansion is not the same as a spaceship engine, but it shows why relativity is more subtle than a simple speed sign in the sky. The Alcubierre idea uses that subtlety. It does not say a ship punches through light speed like a bullet. It says the geometry around the ship is arranged so the distance itself behaves differently. In a quiet mental picture, you might imagine a small island of flat water, with the current ahead drawing toward the island and the current behind flowing away. The island is not racing across the water in the ordinary way. The pattern of the water is doing something stranger. But the price of the original warp bubble is severe. The Alcubierre metric requires exotic energy conditions, often described as negative energy density. In ordinary life, energy is positive. A warm stone, a moving spacecraft, a battery, a star, a beam of light, all carry positive energy. Negative energy is not simply antimatter, and it is not a substance sitting in a tank. Tiny negative energy-like effects can appear in quantum field theory, such as in the Casimir effect between very close conducting plates, but nothing like a practical, ship-sized supply of negative energy is known. The Casimir effect is one of the reasons the warp drive question has never completely disappeared. Quantum fields do not behave like empty classical space. Even a vacuum has structure. Under special conditions, the vacuum between surfaces can have a pressure difference compared with the surrounding region. Physicists can measure this effect, but the measured laboratory phenomenon is unimaginably small compared with what a grand spacetime bubble would require. It is a whisper of the right kind of strangeness, not a working engine. Energy is only the first difficulty. A warp bubble also raises questions about control, causality, horizons, radiation, and stability. If the bubble is moving faster than light relative to distant observers, can the crew inside steer it from the front? Could signals reach the edge of the bubble in the required way? Would particles swept up along the path become dangerous when the bubble stops? Would quantum effects destabilize the geometry? These are not engineering inconveniences. They are deep questions about how space-time, information, and energy fit together. This is why careful language is important. Warp drives are not established technology, and they are not known to be physically possible. They are mathematical possibilities and speculative research programs at the edge of general relativity. A paper can show that a certain space-time geometry satisfies part of Einstein's equations, or that a modified version reduces an energy problem without showing that nature allows engineers to build it, launch it, steer it, or keep it stable. In 2011, Harold White revisited warp field ideas and discussed whether changing the bubble geometry could reduce the energy requirement. One image from that line of work is the idea of a ring-shaped, torus-like distribution around the spacecraft. A different shape could, in principle, make the mathematics less brutal. The thought is gentle but important. Sometimes the geometry of the problem matters as much as the size of the engine. Still, reducing a requirement from impossible beyond imagination to merely astronomical does not make it practical. In 2021, newer theoretical work reopened the discussion in different ways. Eric Lentz described soliton-like spacetime structures that, in the mathematics, could use positive energy rather than the negative energy of the original Alcubierre model. Around the same time, Alexei Bobrik and Gianni Martire developed a broader model of warp-drive spacetimes, including positive energy sublight versions. These papers are not blueprints for near-future starships. They are attempts to map the territory more carefully, to ask which parts of the old dream were artifacts of one mathematical choice, and which problems remain fundamental. The answer, for now, is both hopeful and humbling. Some versions of a warp-like geometry may be less impossible than the earliest headlines suggested. Positive energy models are mathematically interesting. Sublight warp bubbles may be a cleaner subject for physics than faster-than-light bubbles. But the energy scales remain enormous, the construction methods unknown, and the superluminal versions still press against the hardest boundaries in relativity and quantum theory. To feel the scale, return to the nearest star. Proxima Centauri is a little more than 4 light-years away. A beam of light leaving Earth would need more than 4 years to arrive. A spacecraft traveling at 1/10 of light speed, already far beyond our present practical ability for a crewed mission, would need more than 40 years, not counting acceleration, slowing down, shielding, life support, and navigation. At 1% of light speed, the trip becomes centuries. Even reaching such fractions of light speed would demand technologies far beyond current rockets. That is why more ordinary interstellar engineering remains important. Fusion propulsion, powerful lasers pushing light sails, nuclear electric systems, magnetic sails, and long-lived robotic probes may arrive much sooner than anything called warp drive. They do not break the light barrier. They accept the universe as it is and try to move through it more wisely. A small sail pushed by light, a fusion-driven probe, or a patient robotic explorer could transform astronomy long before spacetime engineering becomes more than mathematics. There is also a quiet lesson in time dilation. If a future spacecraft could travel close to light speed without crossing it, the crew's clocks would not match Earth's clocks. Relativity allows different paths through space-time to accumulate different amounts of time. For travelers moving extremely fast, a journey could feel shorter on board than it appears from Earth. This does not solve the whole problem, because Earth would still wait through the long outside time, and the energy requirements would be immense. But it shows that even without warp drive, relativity already makes interstellar travel stranger than everyday motion. Warp drive also connects to the deeper question of quantum gravity. General relativity describes space-time beautifully on large scales. Quantum theory describes fields and particles beautifully on small scales. A real warp bubble, if it requires extreme space-time curvature and quantum vacuum effects, would live where those two theories must speak to each other. We do not yet have a complete tested theory of quantum gravity. Until we do, some warp drive conclusions remain provisional, like shadows cast by two incomplete maps. So could we build a warp drive? Not now, almost certainly not in the near future, Perhaps not for centuries, and perhaps never in the faster-than-light form imagined by fiction. But the question is still useful. It teaches the shape of the light speed limit. It teaches that space-time is not a rigid stage. It teaches that the universe can expand, curve, ripple, lens light, stretch time, and hide distances behind horizons. It shows how a dream can become a mathematical question, and how a mathematical question can reveal the edges of known physics. The beauty of the warp drive idea is not only that it promises a shortcut to the stars. The beauty is that it makes the stars feel real enough to want a shortcut. It asks us to measure the distance honestly, to respect the speed of light, and then to look again at space-time itself. Even if no ship ever rides a warp bubble, the search teaches us how strange the universe already is. Near the end of this journey, imagine a spacecraft resting in orbit above Earth, not yet a warp ship, only a machine made by patient hands. Beneath it, oceans turn in sunlight. Above it, the Milky Way crosses the dark. Somewhere in that band of stars is Proxima Centauri. Farther still are nebulae where new suns are forming, black holes bending light, galaxies moving with the expansion of space, and ancient photons arriving after journeys older than human memory. For now, the stars remain distant. The light speed limit remains firm for every local traveler we know how to describe. Warp drive remains speculative, beautiful, unfinished mathematics. And yet the question itself is a kind of vessel, carrying the mind outward from engines to space-time, from speed to distance, from fiction to physics, and from the small world beneath us to the wide, quiet architecture of the cosmos.